Okay, so we're doing chapter 3, starting chapter 3 today. So chapter 3 is a little bit longer, so we're going to take 2 weeks to cover it. I split it into 2 parts, 3A and 3B, so there'll be 2 sets of homework questions for chapter 3 as well. I believe those are due Sunday once again, so no assignment due Wednesday. So this is going to be the chapter 3A questions. And discussion. Eraser. All right. So we're going to start with talking about types of bonds. So we're kind of carrying this over from chapter 2 when we talked about bonding a little bit when we got into valence electrons. We said valence electrons, those electrons in the outer shell, those were the electrons that are going to be used in bonding. So when I'm talking about electron sharing, electron transfer, the electrons I'm talking about are the ones in those valence shells, the ones in those outer shells. Okay? So we're going to start by looking at covalent bonds. So there's 2 types we're going to explore, covalent and ionic. So covalent, this is when electrons are shared. Okay? It typically occurs between either 2 nonmetals or a nonmetal and a semimetal. So a lot of times you can figure out that it's a covalent bond just based off of where the elements are on the periodic table. So remember on the periodic table we had that zigzag line where the nonmetals were to the right of it and the metals were to the left, and then anything touching that zigzag line was a semimetal or metalloid. Okay, so it typically happens between nonmetals and semimetals. There are a few cases with a metal and a nonmetal, but not very often. Okay, so how do we figure out if it's a covalent bond other than what elements are involved in the bond? We're going to actually use electronegativities to calculate. So there's 2 different types of covalent. There's polar, where the electrons that they're sharing, they're not sharing them equally. Okay, so if they're not sharing them equally, what that means is one of the atoms in the bond is more electronegative than the other one. So it wants those electrons more, and it's going to be pulling those electrons towards it. Okay, so the nonpolar covalent, on the other hand, would be where their electronegativities are very similar, and they're going to share those electrons equally. And when you watch the PowerPoints, you'll see some actual pictures of this occurring so that you can see the electron cloud with both of these types of examples. Okay, what we're going to do today, though, is calculate the electronegativity difference to figure out if a bond is polar or nonpolar. So with that, you guys probably need an electronegativity table so you can help me. I did print some off. These are posted on Blackboard as well for everyone virtually. So it is the link that says electronegativity table and polyatomic ions. They're both on the same sheet. I'm not sure if we'll talk about polyatomic ions today, but we'll definitely get to it on Wednesday. So using this electronegativity table, so it's a periodic table, except for instead of having the atomic numbers and the average atomic mass on it, instead there's just a number below each element symbol, and that number is its electronegativity value. So these are the values we're going to use to calculate the electronegativity difference, and then using that we can classify the bond as either polar covalent or nonpolar covalent. So here's the equation that we're going to be using. So this delta, or this triangle, it's called a delta sign. Delta En, that just means change in. So change in, and then En being electronegativity. Okay, so notice I have absolute value bars on either side of the equation. What that means is when I calculate it, it's going to be positive. If you happen to get a negative, just change it to a positive. The number itself won't change, just the sign. So we're going to take the electronegativity of one atom and subtract it from the electronegativity of the other. Whatever we get, we're going to use this scale below to figure out the type of bond. So if the answer we get is between 0 and 0.5, it's nonpolar, because this would mean that its electronegativity difference is very small. And so if they have similar electronegativities, it would make sense it's nonpolar, and they would share equally. However, if it's between 0.5 and 1.9, in this case, the electronegativity difference would be larger, meaning one atom wants that electron more. It's not going to share those electrons equally, and it's going to be polar. And then you can also use this to figure out if it's ionic, ionic having the highest electronegativity difference. Most of the time for us, we're just going to be like, oh, well, it's a metal and a non-metal, it's ionic. Okay? But you can use this calculation to figure that out as well. So let's look at some examples. So I did 3 examples here. I did them in slightly different formats because you can ask these questions in different ways. So for the first one, I have Si and Cl. So this dash between them is indicating that they're bonded. So you would look up silicon on your electronegativity table, and you would look up chlorine and subtract their electronegativity values. So their delta En. What is silicon?
2.58.
0.58, and then...
Oh, no, sorry, 1.90.
What about chlorine?
3.16.
So to me, this looks like it's going to be quite an electronegativity difference. I would guess that that bond's polar. What do we get when we subtract those two?
Negative
1.26. And since it's absolute values, we just change that to a positive. So 1.26 would be the electronegativity difference. So we look at this range. 1.26 is going to be in the polar range. So this is going to be a polar bond. Polar covalent. What that means is they are not sharing the electrons equally. Okay? Looking at it, chlorine is more electronegative than silicon. So what that means is chlorine wants the electrons more, so he's pulling the electrons away from silicon. They're still sharing them, but chlorine's going to have more of them. So it's going to be, he's going to be slightly negative. I can't draw the delta. Delta negative, and then this would be delta positive. What that means is chlorine's going to be partially negative because he wants the electrons more. Silicon would be partially positive because those electrons are being unequally shared. All right, so the next one is sulfur and oxygen. And I haven't even calculated these yet, so I'm not sure what the answers are. So sulfur has an electronegativity of 2.58. Oh, so you're looking at the second one. And then oxygen.
3.44.
Oh, this is going to be a close one, isn't it? We get negative again, but we just are going to change it to a positive. So we get when we subtract those.
Negative 0.86.
0.86. Okay. So looking at the table again, 0.5 at alk is polar, so 0.8 would mean this is a polar bond.
So the oxygen would be the delta negative since it's higher.
Yes. So oxygen has a higher electronegativity. It wants those electrons more. So he would be partially negative, and then the sulfur would be partially positive. I don't know if you're actually asked any questions. When I looked at the homework, you're not asked questions on who's delta negative, who's delta positive. You're just asked to figure out the type of bond. But sometimes it helps to know the reason behind. So whoever is more electronegative negative is the delta negative. So this next one, I wanted to show an example like this because these questions can be asked different ways. So if I give you NH3 and I say, what type of bond is present? Okay. What I'm asking is between nitrogen and hydrogen. It doesn't matter that there's 3 of them. Okay, you're just looking at that bond. So you're going to calculate it the same way you did up here. Don't multiply anything by 3 because there's 3 hydrogens. I've seen people do that in the past. We're just saying this bond here, is it polar or is it non-polar? Between nitrogen and hydrogen. So we're going to calculate it the same way. We're just going to have 2 electronegativities. So we're using this equation here, subtracting. So we look up in the table. We probably need a table, huh? So we're using that table there, the periodic table. And we're finding the elements present in the bond, in this case, nitrogen and hydrogen, and subtracting them. So what's nitrogen?
3.04.
So nitrogen's more electronegative in this case. It's got a higher value.
It's 0.84.
0.84. I didn't pick a wide range, did I? They're all polar. So this one, 0.84, how do I know it's polar? I'm using this scale. So if it's above 0.5, it's going to be polar. 0.8 is above, so this would be polar. And we just said that nitrogen was more electronegative. I'm drawing those delta signs. So he would be partially negative, and then the hydrogen would be partially positive. I want to do erase the top one just because I'm going to do one more. Let's do polyatomic. What haven't we done yet? This is kind of a different one. So say I have Br2. So this subscript here, that means I have 2 atoms of bromine. So the subscripts are always telling me how many I have. So it's similar to this one down here. I'm just asking what type of bond is present in that molecule. So bromine and bromine. So you're just figuring out the electronegativity difference. This one kind of fools people sometimes. So what's the electronegativity of bromine? 2.96, and you're subtracting it from bromine, 2.96. So when you subtract that, your electronegativity difference is 0, right? So since they have the same electronegativity, it's going to be nonpolar. They're going to share those electrons equally. Because no one wants them more than the other one, they want them the same, so they're going to share equally. So this one would be an example of nonpolar. And usually, when we have a nonpolar covalent bond, we usually just call it covalent. So nonpolar is usually covalent bonds, and then we have polar covalent bonds. Any questions on this?
So on number 3, when we have the NH3,
Yes.
but see, but on number 1 we had the Br2, but since we didn't have another symbol, we just did Br minus Br, because we didn't do anything with the 3.
Right. So once we get further into the chapter, we're going to draw these molecules. And what NH3 looks like is this. It's got 3 hydrogens around it.
Okay.
So if I'm looking for whether the bond is polar or non-polar, I only need to look at one bond.
Okay.
All the 3 bonds are the same.
Okay. Okay.
So we don't know how to draw these yet, so it's a little confusing now, but we're going to learn how to draw them towards the end of the chapter. Any other questions? I'm just going to erase this section. I'm still writing over there. We're still going to stick with covalent bonds, but now we're going to name them. So and all this stuff, all these definitions are in the PowerPoints as well. You can write them down. So with naming, we have prefixes. So we're going to have prefix, element name, prefix, second element, with an ID. All right, so covalent bonds. When you know it's a covalent compound, whether it's polar or nonpolar covalent, you're going to name them the same, as long as it's classified in the covalent area. So when you're naming them, we're going to use prefixes, and we're going to use IDE endings. Okay? So I'm going to write the list of prefixes over here. And you have a list of prefixes in the PowerPoints as well. So the prefixes are used to tell us how many of each atom are present in the compound that we're naming. Okay, so if you have 1, it's going to be mono. 2, your prefix will be di. 3, tri. 4, tetra. 5, penta. 6, hexa. 7, hepta. 8, octa. So we have 9, nana, and I think that's all we don't ever go past 9 in this course, so I'll stop there. For the IDE ending part, we're going to take the element name from the periodic table and we're going to add an IDE ending to it for the second element present. Okay, so what do I mean by that? Easiest way is to just show an example of it. Okay, so I'm going to make a list here. These are chemical formulas. And I'm trying to do ones different than you see on the PowerPoints, just so you get a variety. So you might want to look on the PowerPoints to get other examples. These ones are different. So these are all covalent compounds. Whether they are polar covalent or non-polar, it does not matter when we're naming. Okay, we're still naming them the same. So how do I know they're covalent? Well, they're all either non-metals or semi-metals. Okay, you'll see no metals here. So that's a way to figure out if it's covalent or not. When we are naming covalent, we use prefixes like the ones over there. The prefixes are based off of how many. So what that means is these subscripts, these are going to be our prefixes. Okay. A lot of times, if there's not a number after the element, so in this case SF5, there's no number after S, the sulfur. So we assume that there's just one of them. Okay, I'm going to put a 1 there. So in order to name these, we need to know what elements we're looking at. So that first one, we have sulfur, S, and oxygen for O. Since it's covalent, we're going to use prefixes. So let's start with the first element, sulfur. What should its prefix be?
Di.
Di, because of the 2 after it. Okay, so this is going to be di, and it doesn't have to be capitalized. I just capitalize it. Okay, it can be all lowercase. And then now, after the di, we're just going to put the element name, just how it is on the periodic table. So sulfur. I'm going to spell it wrong. Is it U-R? Either U-R or E-R. I always U-R backwards. So disulfur. So that's the first part of the name. The second part of the name, I'm going to use a prefix again, but this time it's the prefix for the second element present. So how many oxygens are there? 4. So the prefix is going to be tetra. So we're looking at this list over here. And then notice the second element, where you don't write its name as a whole. We're adding an IDE ending for the second element. So oxygen is going to become oxide, right? So this is where it gets tricky, because some people want to write oxygenide. Okay, we're not using the word oxygen and then adding an IDE at the end of that. A lot of them change. So I do have a list for you to look at how each of the nonmetals change with an IDE ending on them. So you can use that, and that's on the PowerPoint. So this here might not be an inclusive list, but I'm just trying to quickly. Sulfur becomes sulfide, so on and so forth. So these are the IDE endings. And I know there's more than that, but there's just a sampling, so you can kind of see how they change. Okay, let's try to name the next one. This one's, I like to throw a curveball after we name one, right? So we have SF5. All right, so we're going to start. Prefix. How many sulfurs are there? 1. So the prefix would be mono. And then it's sulfur again. The first element we don't add an ending to, we leave it just how it is on the periodic table. The second element, fluorine, how many? Penta, 5. Yep, and then fluorine needs an IDE ending and it becomes, I always spell fluoride going to, I think I got it that time, fluoride. So notice my IDE ending. Now, you think, oh, okay, I'm done. No, this is actually incorrect. Why? What's incorrect about it?
Mono.
The mono. So there is a rule that says for the first element, If there's only one, so if mono, don't put prefix. Okay, and if you haven't watched the PowerPoints yet, it might make more sense if you look at CO, for instance. You actually know what this is, you've heard of it. It's carbon, and then oxygen. There's only one, so we would write monoxide. So carbon monoxide. We don't say monocarbon monoxide, we say carbon monoxide. Because if there's only one of the first element, we don't put the mono. And so that same rule is going to apply to this one, because for the first element present, sulfur, there's only one, so we're not going to put the mono. Okay, we do put the mono on the second one if there's only one, on the second element present, but not on the first. So I'm going to erase that mono, and the actual name is sulfur pentafluoride. So our next example, notice, silicon, how many?
One.
Just one. Are we going to put the mono?
No.
No, because it's the first element present. So I'm just going to write the name, silicon, just how it is on the periodic table, no mono because it's the first one present. Chlorine, how many?
4.
4, so prefix would be tetra, and chlorine becomes chloride. We have our IE ending again. And you don't need a huge space between them like I do, it's just because I'm doing it on the board. You can write them close together. All right, let's try C3H8. So in this case, carbon, how many?
3.
Are we going to do a prefix?
Yes.
Yes. So the only time you don't is if there's just one of them. So 3 is what prefix? Tri. And then carbon stays the same, just how it is on the periodic table. We need a prefix for our second element. 8 is octet. And then hydrogen, since it's the second one, we want to change it to hydride. You can see on the list over there, it's not hydrogenide, it's hydride.
I have a question.
Yes.
Would you kind of like on a PowerPoint, it had one of the examples where it was 2, like the valves or whatever, and then it said drop one and just use the O instead?
No, so you're talking spelling. Yes. No, so like here, this is the incorrect spelling because you should, there's an A and an O together, so it should just be an O.
Okay.
I don't spell it right, so if you add an extra letter, that is not affected at all. So she's just referring to if there's 2 vowels in the PowerPoint, I talk about how you just put one of the letters instead of both the vowels right next to each other. But as you can see, I don't do that because I'm not good at spelling. And I'm not going to count you out for not spelling incorrectly either. If you put hydrogenide versus hydride, now that would be an issue. But not the 2 vowels. I do want to do one more before we move on. You can see, erase the top one. All right, so how many nitrogens are there? 1. How many oxygens? 1. So if there's no numbers there, you just assume it's a 1. So how do we name the nitrogen?
Nitrogen.
Just nitrogen. There's only one of them, so we're not going to put a prefix. No IV ending, because nitrogen is the first element present. Oxygen is going to be, we do need a prefix on oxygen. There's only one of them, but it's the second element present, so we have to put the prefix. So mono, and then IV ending, monoxide.
Yeah.
Just like carbon monoxide, right? Except for this time we have nitrogen with oxygen, so nitrogen monoxide. Honestly, I don't even know if that is a real compound, but we can name it. So, all right. Questions on the naming? Because what we're going to do now is I'm going to give the names, and then we're going to change it into a chemical formula. Okay? You need to be able to go both directions. So, go ahead and erase. We're still sticking with covalent, so we're still looking at nonmetals, some metalloids mixed in. But now, I'm going to write up a couple names, and we'll figure out what the formula should be. And these actually are kind of nice. That's what the prefixes are helpful for. So if I have diphosphorus, so if you're approaching a problem like this and you don't know what type of compound it is, whether it's covalent or ionic, the prefixes give it away. We only use prefixes when we name covalent. We're going to do ionic next, and we're not going to use prefixes anymore. So if you see prefixes, you're like, okay, that's covalent. So how do I change it into a chemical formula? You look up both the elements present. So you look up phosphorus, find its symbol. Look up bromine, because that's what bromide is. It's just bromine with an IE ending. And find its symbol. So phosphorus' symbol is P. P.
P. O.
And then bromide, or bromine, I should say, BR. BR. Now you're not done. That's what the prefixes are for. They tell you what numbers, what subscripts are going to go here. So di tells me 2. So that means there are 2 phosphorus atoms in this compound. Looking at the prefix before bromine, in this case tetra, tetra says 4. So I'm going to put a 4 subscript after bromine. 2 phosphorus, 4 bromines. So as long as you know what the prefixes stand for, you can figure out the amount of each. Try the next one. Nitrogen, and we have sulfide, which is just sulfur. So nitrogen symbol,
N.
N, sulfur,
S.
S, and then now we just use the prefixes to tell us what the subscript should be. So how many nitrogens?
2.
2, that's what the die says. How many sulfurs?
1.
1. And when there's 1, you don't actually put the 1 there. You just leave it. 2 nitrogens, 1 sulfur. All right. Last but not least, nitrogen trihydride. Nitrogen, once again, we already know it's an N. But how many?
1.
1. There's no prefix on it, so we know there's just 1. Because remember, we can't put prefixes on the first element if there's only one of them. So that's why the mono's not there. The second part, trihydride, hydride is just hydrogen. So we're looking at the H. For how many? We're looking at tri.
3.
3, yes, good. So these ones aren't too bad because it gives you all the information in the name itself. The only thing you have to look up if you don't know are the symbols themselves. So like if you didn't know the symbol for hydrogen, you would have to look on the periodic table and see the name. Or bromine, for instance, BR. Questions on this? This is it for covalent. So you've learned how to name covalent compounds and how to come up with chemical formulas. So these are chemical formulas. Just so you can get the terminology. If they ask you for chemical formula, you know this is what they're looking for. Symbols with the numbers. All right. What we're going to tackle next is ionic. So we're away from sharing. We're not sharing electrons anymore. Now we're going to look at transferring electrons. So ionic bonds. Now, ionic bonds are typically metals with nonmetals. That's not the only possible scenario, but that's where we're going to start. We're going to start at looking with just main group metals and nonmetals combined. Okay, so this is where we have a transfer of electrons. So that means ions are going to be involved. So last chapter, chapter 2, we talked about ions, right? Lithium +1 and chlorine -1. So if they had lost an electron or gained an electron, they formed an ion. So that's what we're going to see here. We're going to see a positive ion and a negative ion make an ionic bond because opposites attract. So the pairs that we're going to see, the metals and nonmetals, we're going to have a positive metal ion and a negative nonmetal ion. Because remember, the metals like to lose electrons, so they will be positive ions, cations, if you will. The nonmetals like to gain electrons, so they're going to be the negative ion, or the anion. So, let's look at how we're naming these. Now notice the metals, that zigzag line, we said they were to the left of the zigzag line. So we're looking at a very large portion of the periodic table. Okay, so these get a little bit complex when we name them. There's more possibilities, there's more types. And we're going to start off with the simplest type. We're going to look at binary ionic compounds. So when I say binary, 2 elements involved. Okay, then we'll increase our spectrum and look at the polyatomics, and then we'll even bring in the transition metals. But let's start here. So binary ionic compounds, meaning 2 elements present. That's what the bi means. All right, so first key, no more prefixes. Prefixes are only for covalent compounds. We're not talking covalent anymore, we're talking ionic, so I don't want to see any di, tris, tetras. All right? How are we naming them? Different colors here. We always name the positive ion first, or the cation portion. And we're just going to use its element name straight from the periodic table. No prefixes, no alternate endings. Then we're going to name the negative, or the anion portion. So the negative ion next. And on the negative ion, we're going to have an IDE ending, much like we did when we named covalent. So positive ion, straight off the periodic table, then we're going to name the negative ion, and the negative ion is going to have that IDE ending. So metal, non-metal with IDE. All right, so let's throw up some examples. Name them. BaCl2, 3. I almost said the name of it. Just looking at it. So BaCl2. So you're just going to look up the symbol Ba. In this case, it's an alkaline earth metal in group 2. So its name is barium. So that's the metal portion, right? We said it was an alkaline earth metal, group 2. Cl, that's chlorine. Okay, does it matter that there's 2 of them? Not to name it. It doesn't. I'm not going to do dichlorine. Okay, so no more prefixes. So chlorine is the negative ion portion or the nonmetal portion. So we need to add an IDE ending to it. So chlorine becomes chloride. That's it. It's named. The next example, I have 3 RBs. This does not matter that there's 3 of them when we're naming it, okay? Because we're not including prefixes anymore, so it's not going to be tri. So we just look up RB on the table, and it is an alkali metal. So it's going to form a positive, a cation. It's going to lose electrons. So RB is rubidium. I might have spelled it wrong, but my periodic table over here doesn't have the names on it, so I have to try to remember. So rubidium. Now the second element present is going to be the negative ion, the nonmetal portion. So we're going to add an IDE ending to it. So N is nitrogen, so nitrogen becomes nitride. Yes. Right. So we're not going to name a lot of these because, as you can see, there's not much to it. We're not worrying about prefixes. Only thing you need to make sure to do is add an IDE ending to the second element. What I'm going to focus on is taking the names and coming up with chemical formulas, because it's a lot harder for ionic compounds to do that. So I'm going to do more examples of that instead. So I'm going to write some names over here. Separate examples. Number. More examples over here in a minute. We'll start with those two. So, the thing that's difficult about taking the name of an ionic compound and coming up with the formula is we don't have prefixes anymore. So it doesn't tell us in the name, hey, there's two of these guys, by putting a di there. So we have to use their charges, their ions, to figure it out. Okay? So these compounds are neutral overall. What that means is the positive ion and the negative ion cancel each other out. So that's our goal, is to figure out how many we need of each to get it to be neutral. So to do this, we're going to look up beryllium on the periodic table. Be, so it's number 4, its atomic number is 4. It's an alkaline earth metal. We learned last chapter that anything in group 2 had what charge? +2. It's going to lose its 2 valence electrons to become a +2 cation. That's everybody in group 2. So I write the symbol with the charge. That's your first step for each element present in the compound. So next, I'm going to do hydrogen. Now this one is tricky, because hydrogen can be a +1, but it can also be a -1. So how do I know what it is in this case? Because it's the second element present. So I said the second element present is the anion. It's the -1. So in this case, we're talking about hydrogen with a -1 charge. Because I need a cation with an anion. I'm not going to have 2 positively charged ions make a compound, because if we had the same charge, they would repel each other. We need opposite charges so they can attract each other. Okay? So in this case, if I had just 1 beryllium and 1 hydrogen, do their charges cancel? So if I take a +2 plus a -1, do I get 0?
No.
No. So what do I need more of? Do I need more hydrogens or more berylliums?
More hydrogen.
More hydrogens. So let's add another one. Now it works, right? So on my anion side, I have a total of a -2 charge. Right? -1 plus a -1 equals -2. On the beryllium side, I have just one of them for a total of a +2 charge. So now it's neutral. Since it's neutral, that means I need 1 beryllium and 2 hydrogens. To represent that in a chemical formula, I would write Be, and there's just 1, and then hydrogen with a 2 as the subscript, because I have 2 of them. All right. So let's try another one. Sodium sulfide. So sodium, we need to find its symbol and its charge. Sodium is an alkali metal in group 1. Na is its symbol. Since it's in group 1, its charge is +1. What about sulfide? So sulfide is just sulfur. So it's S, and the charge was what? -2. Okay, so it is in group 16 on the periodic table. It's 2 away from being a noble gas, so it gains 2 electrons, making it a -2 charge. So now, it's not neutral how it's written, right? Their charges aren't canceling. Do we need more sodiums or more sulfurs? More sodium. So if I add another sodium, now they'll cancel, right? Because I have a +2 on the cation side total, and a -2 on the anion side, making it neutral. So when I write this, I have 2 sodiums, so I would write Na with a 2, saying there are 2 sodiums. And then for sulfur, I just have 1. So just leave it with a S and no number after it. Now, I always show you the long way first, and then I show you a shortcut. So there's a shortcut to this, where you don't have to write them all out like that. Let's look at the next example to see that shortcut. Let's do, I'll do rubidium papers. That's fine. So aluminum oxide. So let's find the ions. Let's find the symbols with the charges. Aluminum is a metal. It's on that zigzag line, but it's not a metalloid, it's a metal. What charge does aluminum have? +3. So since it's a metal, we know it's going to be a cation. We know it's going to lose electrons. Since it's in group 13, it's a +3. It has 3 valence electrons that it loses. What about oxide? Is oxygen. So it's O. What charge? -2. Just like sulfur. Oxygen and sulfur are in the same group, so that's why they're both -2. They both gain 2 electrons to get their full octet. So we could do the list, try to even it out. What's the shortcut way? It's called the crisscross method. It's where you take the number of the charge, so I'm not going to take the plus sign, but just the number, and make it a subscript on the opposite element. So I'm going to put 3 oxygens is what I'm saying. Now I'm going to take the charge on the oxygen, just the number, not the negative sign, and that's going to become a subscript on the aluminum. So I'm saying I need 3 oxygens and 2 aluminums. So this gives me Al2 and then O3. Now, if I wanted to write that out to make sure it was neutral, it would look like this. Because I have 1, 2, 3 oxygens for a total of -6. Following me so far? 2 + 2 + 2, total -6 on the anion side. We said 2 aluminums. I have 2 aluminum atoms written here, each with a +3 for a total of +6. So yes, it is neutral that way. So I could have done it this way where I wrote them all out, or you can just crisscross them. And you're going to get the same answer no matter what. With the crisscross method, once in a while you get an answer that you have to simplify down. So what I mean by that is, let's look at what that would look like. So let's do sorry, I know I'm skipping this one, but since I just said the crisscross method, sometimes you have to simplify down. I wanted to do an example like it right away. So strontium is Sr. It is +2 because it's an alkaline earth metal. Oxygen we just saw was a -2. What are you noticing with the charges? They cancel right away. So what that means is you only need 1 of each, right? But if you didn't realize that and you did the crisscross method, the formula that you would come up with using the crisscross method would be Sr2O2. And that's incorrect because we don't need 2 of each, we just need 1 of each. The correct answer is just SRO. So if you do the crisscross method, you need to double check and see if you need to simplify it further, do so. What that means is I have 2's here. So if I divide both of these by 2, common denominator, right, I can simplify it down to SRO. So crisscross method, you might need to simplify it down. So if you want to use this longer method, you never have to simplify that one down. That one works with the correct formula every time. All right, so that was a random aside, so let's do this last example that I have up here. So rubidium phosphide. So cation comes first, the metal comes first. Rubidium is Rb, is that right?
Yes.
It is alkali metal, number 37 on the periodic table, so it forms a +1. Phosphide, that's just phosphorus. Phosphorus is in group 15. It's actually number 15,
-3.
It's a -3. So everybody in group 15 forms a -3 anion. Nitrogen, phosphorus, arsenic, all those guys. So it's not neutral how it is. Do I need more of the cation or more of the anion? Cation. I actually need 2 more. So I need a total of a +3 charge on the cation side to cancel out the -3 charge of that phosphorus. And you could have also done the crisscross method here as well, where the 1 becomes a subscript on the phosphorus, the 3 becomes a subscript on the rubidium. Okay, so what we get is 3 rubidiums, so Rb3, 1 phosphorus. So this would be the correct chemical formula of that compound. I'm running out of time, aren't I? Yep. So, it's actually a good spot to end because we've covered ionic with main group metals. Notice all the metals we've looked at are the main group, the representative elements, with nonmetals. So when we come back on Wednesday, what we're going to do is we're going to add polyatomics into the mix. And that is where we're going to need our polyatomic tables, which is the second